In this video, we're going to learn how to evaluate limits that are of one of these indeterminate types. So these are all indeterminate types where we have an exponent. So maybe of type 0 to the 0, infinity to the 0, or 1 to the infinity. As we already said in class, these are all indeterminate, meaning that they could take lots of different values. And we'll see this partly with the examples that follow. And you'll see this when you're doing the exercises that were assigned on WebAssign. Before I explain the method for evaluating limits of these indeterminate types, let's just recall some facts about the exponential functions and the logarithmic functions. In particular, if you take the log of an exponent like this exponent b here can be brought down in front. So this is b log a. Also, the exponential function and the logarithmic function are inverse functions. So e to the log y is equal to y for any positive value y, any y in the domain of this our natural log function, and the natural log of e to the y is equal to y, and this is for any y in the domain of the exponential function, which is to say any real number y. All right, so here is the method that we'll use to calculate a limit as x tends to a, that a could be plus or minus infinity, of f of x to the g of x when this limit is one of the indeterminate types that we mentioned above. So what are we going to do? Well, we're going to start by letting y equal the function we're interested in. So we'll let y equal f of x to the exponent g of x. Well, then note that the log of y, well, that's the log of f of x to f of x to the exponent g of x. And remember, we can just take this exponent down in front of the logarithm using the rule of logarithm that we mentioned up here. So this is equal to g of x times the log of f of x. Now what are we going to do? Well, now, remember, we want to know the limit as x tends to a of f of x to the g of x. In other words, we want to know the limit as x tends to a of what we've called y. Instead, we're going to start by calculating the limit as x tends to a of the log of y. And we'll be able to do this using our earlier methods. So suppose that we calculate this limit and we obtain a value of L. So usually this is going to be a limit of type 0 times infinity, though not always. Usually type 0 times infinity, and we already learned, in fact in the last video, how to evaluate limits of type 0 times infinity by rewriting such a limit and then applying L'Hopital's rule if necessary. Now we can evaluate the limit that we're interested in. So remember, we are first interested in the limit as x tends to a of f of x to the g of x. Well, f of x to the g of x is what we called y. So we're looking for the limit as x tends to a of y. And we're assuming that at this point we've evaluated the limit as x tends to a of log y. So we're just going to try to write y in terms of log y. Well, as we mentioned before, because the exponential function and the natural log function are inverses of one another, y can just be written as e to the log y. And now, well, as we said, we know the limit as x tends to a of log y, and in fact the exponential function is a continuous function, so we can write this as e to the limit as x tends to a of log y, which we said we already calculated as e to the L. All right, so that's the method that we're going to use in the next several examples to evaluate a limit of indeterminate type of this form here, f of x to the g of x. Well, we'll let y equal f of x to the g of x. We'll then evaluate the limit as x tends to a of the log of y, rewriting the log of y in this form here using our earlier methods. And then we'll be able to return to the original limit that we are interested. The limit as x tends to a of f of x to the g of x. That was just the limit as x tends to a of y. Y, though, is e to the log y, and we know that log y is tending to L, so this limit is just e to the L. All right, in this example, we want to take the limit as x tends to 0 from the right of x to the root x. Well, let's check and see what type this is. Maybe it's not even indeterminate at all, but what is actually happening as x tends to 0 from the right, this x here is going to tend to 0, and this root x is tending to root 0, which is just 0. So this is of type 0 to the 0, and that is indeterminate. As an aside, you might be wondering, why is a limit of type 0 to the 0 indeterminate? Well, that's not hard to show. In other words, it's not too hard to show that a limit of type 0 to the 0 could take multiple values. For example, if we were to consider the limit as x tends to 0 from the right of 0 to the x, well, this certainly is of type 0 to the 0. And, in fact, for any x bigger than 0, 0 to the x is just equal to 0. So this is just the limit as x tends to 0 from the right of 0, which is 0. All right, so this limit of type 0 to the 0 is 0. What about this one here? Here's another example of a limit of type 0 to the 0. This one is the limit as x tends to 0 from the right of x to the 0. Well, certainly this is of type 0 to the 0, and for each x we're considering here, when taking this limit, x is bigger than 0, and if you take an x that's bigger than 0 and evaluate it to the power 0, you're just going to get 1. So for each x here, this x to the 0 is 1. So this is in fact the limit as x tends to 0 from the right of 1, which is 1. So there we have two limits of type 0 to the 0 taking different values. This shows that limits of type 0 to the 0 are indeterminate. In fact, they could take lots of different values. The same is going to be true of the other types of limits involving exponents that we are going to deal with. And you could give similar arguments to show that they too are indeterminate. I won't give those arguments going forward though. Okay, so let's return to this limit. Remember, it's of type 0 to the 0, so we're going to use the method that we outlined above. So, namely, we're going to start by letting y equal x to the root x. And then we're going to evaluate the limit as x tends to 0 from the right, not of y, but of the log of y. All right, well, this is the limit as x tends to 0 from the right. And when we take the log of y, this is the log of x to the root x. This root x is going to come down in front of the log. So this is equal to root x times the log of x. And now we take a look and see what type of limit is this. Well, the root x is tending to 0 as x tends to 0 from the right. And what about that log x? Well, let's just remember that the log function looks like this. And as x tends to 0 from the right, as we're considering here, log x is tending to minus infinity. So this looks like type 0 times minus infinity. All right, well, we talked about how to deal with limits of type 0 times plus or minus infinity in the last video. And if you recall, what do? We rewrite the limit by putting one of the two factors, either root x or log x in this case, in the denominator as its reciprocal. So put the one that's going to be easier to differentiate as its reciprocal in the denominator usually. In this case, I think 1 over root x should work well. Let's just notice that 1 over root x can be written as x to the minus 1/2 for the purpose of differentiating. Well, why would I differentiate? Well, the reason is because looking at the new limit, as x tends to 0 from the right, log x is still tending to minus infinity, and 1 over root x, what happens to that? X becomes very small and positive. That root x is small and positive. 1 over small positive is very, very large. That limit of the denominator then is infinity. All right, so this is of type minus infinity over infinity, and that means that we can apply L'Hopital's rule to evaluate this limit. This is the limit as x tends to 0 from the right of differentiating the numerator. We have 1 over x, and differentiating the denominator, we have, well, I'm differentiating x to the minus 1/2. That's minus 1/2 x to the minus 3/2. In fact, we evaluated this limit earlier. It was example 5 in the last video, but I'll just quickly repeat this argument. Remember, after applying L'Hopital's rule, in other words, after differentiating numerator and denominator, you always want to simplify your new function before examining it as a limit. How can we rewrite this? Well, this minus 1 over 2x to the minus 3/2 in the denominator, we could write as minus 2 times x to the 3/2, and this over x. And what do we have? This now is equal, simplifying by canceling some x's, the limit as x tends to 0 from the right of minus 2x to the 1/2, which we could write as root x. This limit is no longer indeterminate. The limit as x tends to 0 from the right, we can obtain this just by evaluating root x at 0. And we get minus 2 times root 0, if you like, which is 0. All right, so what do we know? We now know that the limit as x tends to 0 from the right of log y is equal to 0. But remember, this isn't the limit we were interested in. We were interested in the limit as x tends to 0 from the right of x to the root x. That's what we called y. So let's now find the limit as x tends to 0 from the right of x to the root x. Okay, so we now can say the limit as x tends to 0 from the right of x to the root x. That's the limit we were interested in. Well, that's just the function that we called y. So it's the limit as x tends to 0 from the right of y. I'm just using exactly the procedure outlined at the start of the video. This is the limit as x tends to 0 from the right. How can we write y in terms of log y? Because we know the limit as x tends to 0 from the right of log y. Well, we write it as e to the log y. Now, as we said, as x tends to 0 from the right, log y tends to, as x tends to 0 from the right, log y tends to 0. So e to the log y tends to e to the 0. And that's really by continuity of the exponential function. So this is e to the 0. And what was our limit then? Our limit turned out to be 1.